All right, welcome back, everybody. It's day 2 of exam review. So we're here. Compute the following permutations and or combinations. Now remember the difference between permutation and combination. Permutation order matters where combination order does not matter, right? Let me just get out the exam review key. Hopefully I got one. I don't know if I got the exam review key in here.
Yeah.
Uh-oh. I did this in Calc too. Where is my exam review key? Good question. All right. So, part A here. How many ways can you place top 5 from a group of 30 performers? Okay, so does order matter? If I place 1, 2, 3, 4, 5, band A, B, C, D, E, if I change the order of that, is that a different outcome?
Yes.
Yes, that is a different ranking. So that means the permutation, not combination. So I have a total of 30. P5. Remember, we get to that in our calculator by just taking 30 math, PRB, choice 2, 5. So that is a lot, big number. 17 million, 100,000, 720? Yeah. That many different ways. Those 30. So that means like if you predicted the top 5 out of those 30, you have a 1 in over 17 million chance. All right, Sadie has 30 Bluey episodes she can watch, but she only has enough storage for 4 of them on her Kindle. How many different ways can she select her Bluey episodes? Does order matter?
No.
Show episode 1, 2, 3, 4. If I download those 4 episodes and I change the order and I download them in 4, 3, 2, 1, does she still have the same amount of episodes on there? Yep. So 30C4 is my solution. Let's see how many that is. Remember, combinations are always going to be less than permutations. 27,405. So there are over 27,000 ways that she can download those 4 episodes. You're selecting a performance order for a show. You have 10 bands to choose from and you are picking 6 of them. How many different possibilities of lineups can you create? Permutation or combination? Permutation. Permutation. We got 10. 6 of them we're choosing. And again, order matters here. You know, I'm choosing a lineup. So 10 P6. 151,200. Pretty simple bit, right? All right, let's take a look at number 12. Suppose that a coin is weighted so that the probability of tails is 0.65. Answer the following questions, assuming that you flip the coin 20 times. What is the probability that you flip exactly 8 heads? Oh, that's right. This was that weird formula, the binomial theorem formula. Chapter, nope. Chapter 3. Where is this at? Where is this at? Maybe it was further on. Yep. Binomial probability of X successes in N trials. Mid-chapter 4, this one is. Mid-chapter 4. It basically says that if you want to find the probability of X, it's equivalent to NCX, P to the X, Q to the N minus X. Right? And we're not told, this is just straight off the formula sheet, we're not told what all those things are. What is N in this case? 20. What is X in this case for part A? 8, right? So I've got 20, C, 8. What is P in this case? 0.35, because I want the probability of getting exactly 8 heads, right? So probability of getting a head is 0.35. Raised to the X power, which again is 8, times Q, 0.65, to the n minus x. So 20 minus 8 is 12. You follow me there? That's out of these 20 trials. How many times? What's the probability that I get exactly 8 heads? Okay, so 20 C8. 20 C8 times, I've got that's negative, 0.35 to the 8th times 0.65 to the 12th. 0.161. Is that what you guys got? Sure. Sure. That's what we did. 0.161. Okay, what's probably getting 18 tails? More than 18 tails. Excuse me, more than 18 tails. More than 18 tails. All right, so more than 18 tails is the probability of 19 plus the probability of 20. You follow me? Of getting more than 18 tails is the probability of 19 plus the probability of 20. Do I include the probability of 18? No, because it's more than. I didn't say at least 18 tails, but more than 18 tails. So let's calculate the probability of 19. 20 C 19 times 0.35 to the 19th times 0.65 to the first, right? Oh, wait. Tails. We've got these flipped around, don't I? This should be 0.65 because that last one was heads. I'm just trying to copy off that. 0.65 to the 19th times 0.35 to the first. That's probability of 19. Plus, okay, I got to put this whole thing in. 20C20. Which should be what? What's 20C20? 1, right? So I guess I didn't really need to type that in. Times 0.35 to the 20th power. Do I have to multiply anything else? Because it'd be, shoot, I did it again. 0.65 to the 20th power. Excuse me. This is what tails, not heads. 0.65 to the 20th power. And then we would multiply by 0.35 to the 20 minus 20. But anything to the 0 power is 1. So add that together. The grand total of all of these added together is super high, 0.002. A 0.2% chance of happening. Questions about that? Because again, even if the coin is weighted, getting 19 or 20 out of 20 all with heads or all with tails. Okay, calculate the mean, variance, and standard deviation. Okay, mean. Still in chapter 4 here. The mean is NP. The variance is NPQ. So therefore, the standard deviation would be square root NPQ. Pretty simple. Okay, NP. Now, standard getting a tail. This would be different if I had said getting a head, right? Getting a tail. So getting a tail is 0.65. So n times 0.65, 20 times 0.65. It's kind of like the expectation. I expect to get 13. 13. Okay. So I take n times p times q, and that's my variance. So n times p times q, 0.35, 4.55. And I square root that, 2.13. Questions there? All right, let's keep it rolling. Number 13. In chess, games can end in a win, loss, or draw. Let's assume Mr. Laverick's probability of win is 0.55, probability of loss 0.4, probability of draw 0.05. Assume that I play 10 games. Results being independent of one another. What's the probability that I win at least 2 games? Win at least 2 games. Now, do I want to go in and find probability of 2 plus probability of 3 plus probability of 4 plus probability of 5 plus probability? I don't want to do that. So I'm going to do the complement. What's the probability? What's the complement of winning at least 2? 1 minus less than 1, or 1 or less, right? So that means the probability of I want to do this. 1 minus the probability of winning 1 game plus the probability of winning no games at all. Because is that an option? Yeah. Does that make sense? No matter what. I won't continue on with this one. I think there's some expletives right after that, so I'll stop. So probability of 1 plus the probability of 0. Now, probability of 1. Okay. Probability of 1 win out of these 10 games. We're talking about wins, right? Yeah, wins. All right. The probability of 1 win is not 20 anymore, sorry. 10C1. Could have just written 10. 10C1 times, winning 5 raised to the first power times 0.45, the complement, Q, the loss and draw together, to the 9th. Okay, it's probability of 1 plus probability of 0. Okay, math. Oops, sorry, I forgot to put in my 10. 10C 0 times 0.55 to the 0. I guess I could have just left that out. Times 0.45 to the 10. So adding those together, 0.00, let's say 0.0045. 1 minus 0.0045. 1 minus 0.00445 is 0.9955. That's the probability of me winning at least 2 games if I play 10. What's the probability of drawing between 0 and 3 games? Between 0 and 3 games. Oh, inclusive. Oops, inclusive. So that means I say probability of drawing of 0, 1, 2, and 3. Right? So probability of 0. Drawing. Yeah, that's the issue here. I'm changing up that, right? I'm drawing. Okay, so it's 10C10, which is just 1, right? 10C10 times 0.05 raised to the 0 times 0.95 raised to the 10 plus 10C10 or 10C, excuse me. Oh wait, I did 10C10. 10C10 is not what I wanted. I wanted 10C0. Stupid Mr. Laverick. I'm going to take that. I'm going to multiply it by 10C0. Ow, no. Wanted to insert a parenthesis. There we go. Oh, jeez.
Just skip it. It's okay. We get the idea.
You get the idea, right? That'd be a lot for me to punch in the calculator. We understand, though, right?
No, I think you need to go.
No. If we have extra time at the end, maybe I'll do that. You get it. You get it.
Extra time? There's 26 questions. It seems there are going to be 26 questions. How many questions? Oh, 10. I think we can do 140 minutes. I think we can.
Less than 26.
Listen, I'm just saying, I did like 80 art history multiple choice in like 20 minutes.
Yeah, but that's
This is all basically all the tests
This is not
smushed
nice.
together. Is this exam review?
Is any of it multiple choice? Please no true or false. Please.
I honestly can't remember.
Let's just take a look at it.
My memory is gone. Assume that for a continuous or variable x is normally distributed with a mean equal to 42. And a standard deviation equal to 11. Find the indicated probability. All right, probability of greater than 55. Probability of x greater than 55. Okay, first thing I got to do is transfer that to a z-score. So z is equal to x minus, x minus mu over sigma. So I've got 55 minus 42 divided by 11. So 1.18 is my z-score. So then I just have to look and go into my standard normal table, go to my z-score, and look for 1.18. 1.18. So that gives me 1.18. Why do I always make these so hard to read? 0.8810? Okay. 0.8810. Now, watch out. That's to the left of it, correct? Right? That gives me this. Where do I want? The opposite. So 1 minus 0.8810 is what I really want. Which is 0.119. Honestly, guess what number you would have gotten if you looked up negative 1.18?
The same number.
0.1190. All right, and let's do part B. I've got to find the z-score for both of them. So that's 32 minus 42 over 11. So negative 10 over 11. Negative 10 elevenths is negative 0.91. And then we take 60 minus 42 over 11. So 18 divided by 11 gives us 1.64. And now I just find those two probabilities. Because since I want to go in between, I'll take the two probabilities and then I'll subtract them, right? Because this is going to give me a high end and a low end. I want to subtract off the low end. Okay, 1.64 gives me 0.9495. 0.9495. Negative 0.91. 0.1814. 0.1814. All right, take bigger minus smaller. 0.9495 minus 0.1814. And that's going to get me 0.768. So we know there's a 76.8% chance of landing in the 32 to 60. Questions about that? Okay. Number 15, surveys of car owners show that the average age of their car is 10.4 years with a standard deviation of 3.4. Assuming that the length of time is described as normally distributed, answer the following questions. If a single car owner is selected, what is the probability that his or her car is between 7 and 11.3? Okay, so this is basically like the exact same thing that I just did, but now with context to it, right?
Yeah.
Okay, so that means I want to take 7 minus 10.4 divided by 3.4. So our first z-score for 7 is -1. Oh, okay, cool, -1. And our second z-score is 11.3 minus 10.4 divided by 3.4. Our second z-score is 0.26. Okay, so the z-score for -1 flat is 0.1587. 0.1587 and 0.26, positive 0.26, 0.6026. Okay, so now we take 0.6026 minus 0.1587, and that's going to get, oh, there's no minus sign there. Right here is the minus sign. And that gives me 0.4439. Good so far? If a single car owner is selected, what's probably his or her car is more than 8.3 years old? All right, so probability of x greater than 8.3. That's what I'm looking at here. Now, based on average car and standard deviation, I'm going to say it's probably going to be a bigger-ish number. Let's estimate it to be like 0.6. 8.3 minus 10.4 divided by 3.4. The z-score for 8.3 is negative 0.617. Don't think I'm that good. That's just the z-score, not the probability. Negative 0.62. Negative 0.62. And now I go to my table to negative 0.62. Negative 0.62. 0.2676. 0.2676. And because, as Luke correctly pointed out, because it's greater than, I want to do 1 minus. And I am wrong. It's like 73% something. 1 minus 0.2676. 0.7324. Yeah. Company guarantees that their car lasts longer than 92% of their cars on the market. How long will it have to last to ensure that guarantee? Okay, so I am looking for the X value, right? Yeah, 92%. So it's going to last longer than 92%. I want it to be out there, right? Okay, so what is 1 minus, no, 92% is over here, right? So I can look up 0.92. Yep. 0.92 is going to be, let's find it, 0.9207, I'm going to go 1.41. 1.41. Look up 92% within your table. So like 1.41. You follow me? Flip it over one page.
Oh, okay.
Then from there, okay, so I know I want my z-score to be 1.41. You follow me?
Yeah.
Turn that into an x value. So 1.41 is going to be x minus mu over sigma. So that means I'm going to multiply by sigma, 1.41 times 3.4, and then I'm going to add over mu, plus 10.4. Okay, so that means the car needs to last 15.19 years. 15.19 years or more. If a random sample of 15 car owners is taken, what is the probability that the mean age of their cars is less than 10 years? Ooh, okay, so this is different, right? I'm talking about the mean. This is like the sampling distribution thing. That's different. A mean of the sampling distributions. Yeah, right here. If a random sample of 15 car owners is taken, what is the probability that the mean age of their cars is less than 10 years? This is the divided by square root of n, right? I don't think it's in this. Variance, standard deviation of sampling distribution. Yeah, here it is. Right up at the top up here, still in chapter 5. It's going to be x bar minus mu over sigma over the square root of n. That's where this comes in. Okay. End chapter 5. Okay, so x bar is going to be, in this case, 10. Our original was 10.4. Our sigma was 3.4. And my sample size that I chose was 15. So I take 10 minus 10.4 divided by 3.4. Oops, that's a negative. 3.4 divided by the square root of 10. Or sorry, 15, excuse me. Negative 1.85. Now, I go to my z-score table, negative 1.85. Negative 1.85 is 0.0322. 0.0322. Do I need to take one minus? No, because I say less than. Right, so about a 3.2% chance that their mean comes out to be 10, less than 10 years old. Question about that? And again, notice the difference in the type of question. This is asking if I take a sample from these car owners, what is the probability that of those 10 car owners that I chose, or 15 car owners that I chose, that their mean comes out to be less than 10? Because I know the population mean is 10.4. So it should be the same if it's a true representative sample. That's why it's coming out so low. The algebra OST test is taken by freshmen. The scores are normally distributed with a mean of 700 and a standard deviation of 30. High scores are good for this test. What percentage of students should score at least a 682? Okay, so I want to find that percentage, right? Z-score for that. So it's 682 minus 700 divided by 30. Okay, 19.4. Oh, wait. Ooh, I was like, wait a second. That's weird. 682 minus 700 divided by 30. That's much better. Negative 0.6. Negative 0.6. And I go to my z-score table. Negative 0.6 is 0.4761. 0.4761. Do I have to do 1 minus that? Yes, I do. Because I need to score higher than a 682, right? They need to score at least 682. Could they score a 685? Yeah, it's greater than. So that means I got to take 1 minus 0.4761. 0.5239. One of the schools in the county boasts that they have scores in the top 10% in the algebra OST. What score must they have gotten? So they are better than 90% of the other schools, right? 90% of the other schools are down here. So I'm going to go to my z-score table and look for 0.9. Because that's going to tell me the z-score that they should get. So 0.9 flat. Looks like it's 1.28. 1.28 in rounding. Right? So I'm going to turn that into an x. So that's x minus 700 over 30. So we multiply by 30, and we add 700 to that. So 738. Random sample of 50 students is taken. What's probability that the mean of their scores is between 698 and 705? All right, so random sample, that means n is 50. And I want to find the mean, the probability that the mean scores fall between those. Now that, again, is sampling distributions, right? So that means I got to do that other funky formula with the square divided by the square root of n thing. So we're going to take x, which is 698, we're finding each one of their z-scores, minus 700, divided by, now this is where it gets a little weird, the standard deviation, divided by the square root of 50. Okay, so negative 0.47. Negative 0.47, that's 698. Oops, I wrote 688. That's the z-score for 698. Let's find the z-score for 705. So basically 5 divided by 30 divided by the square root of 50. 1.18. Turn those into probabilities. So I've got negative 0.47, which gives me 0.3192. And 1.18. 1.18, which gives me 0.8810. I subtract the 2. Oh, hold on. 0.8810, 0.3192, 0.5618. So we have a 56% probability that their mean score falls in between 698 and 705. I choose 50 people. Bigger sample I choose, the more it's gonna, the more it should tend to go toward my actual mean. How many questions we got total on this?
26.
26. Yeah, we'll keep on moving. The mean GPA at LHS is 2.95 with a standard deviation of 0.62. You take a random sample of 85 students. Honestly, this is the exact same thing that we just did, isn't it? Care if I skip this question? Nope. Okay. If you need to see the answer, the key is online. Okay, confidence interval. This is different. This is chapter 6. Okay, remember confidence intervals are x bar minus e is less than mu, x bar plus e. Oh, wait. And e is equal to zc sigma over radical n. It's all straight off the formula sheet. Okay, e is our standard error, right? Our standard error, which will give us our confidence interval. So we got to find our critical, our zc, right, for our confidence. So 95% confidence interval. Now remember, for these, you can go to your level of confidence little table down here, and I more than likely will give you something right from that's in that table. So the ZC is 1.96 for that. So 95% confidence interval is going to be, the ZC is going to be 1.96. Straight off that tiny little table there. All right, so our error margin is 1.96 times sigma, which is 0.4, divided by square root of n. So we've got 0.4 divided by the square root of 40 times 1.96, and that's going to give me 1.124. Okay, so now I add and subtract my my error margin from x bar. Okay, sample mean of 5.9. So I'm going to take 5.9 minus 0.124 and 5.9 plus 0.124. And that, serious, stop it. Why is that not working? Okay, get out of there. 5.9 minus 0.124, and then 5.9 plus 0.124. So in between 0.5776 and 0.6024. That's my 95% confidence interval for the error margin. Number 19. From a random sample of 24, honestly, that's the exact same thing, isn't it? Yeah. I mean, I think you can see how I'm not going to be asking multiples. I'm giving you multiple examples, but I'm not going to be asking you multiples. A sports statistician claims that the mean winning time for the Boston Marathon and Women's Open Division Championship. Okay, here's different. This is a hypothesis test, right? This is a hypothesis test. This will be the last one we'll do here. What's my null and alternative hypothesis? Okay, what's his claim? Claims that the mean winning time for the Boston Marathon Women's Open Division Champions is at least 2.68. So mean is greater than 2.68. Greater than or equal to, right? The or equal to has to go in there. Okay, so that means mean is less than 2.68. Claim is up here, right? So what's the only thing that we could do? Disprove his claim, right? We cannot support his claim, but we can disprove his claim. All right. Mean winning time of a sample of 30, and it's 30. Randomly selected is 2.6. Assume the population standard deviation is 0.32. And alpha is 0.05. Okay, is this going to be t-score or z-score? Z. It is z. Why? Because standard deviation is, the population standard deviation is known. So it's going to be z-score. So that means I go to my z-score table, and I figure out for the rejection region. For the rejection region, I'm going to look for the alpha 0.05. Now, when I know the alpha is 0.05, I can either look at 0.05 or look at 0.95, right? Either one is going to give me the same z-score. I'll look at 0.05. Negative 1.6. Oh, it's halfway in between those. Negative 1.645. So my critical value is negative 1.645. Now, actually, truly, what is it? What's my critical value here then? Oh no, I'm good. Yeah, because my what's it called? Alternative is less than, right? So ZC is negative 1.645. So that means if Z comes out to be less than negative 1.645, then we can reject. Oh, I don't know if we reject or not. That's our rejection region. So let's figure out what our z-score is. All right. Straight off the formula sheet here. X bar minus mu over sigma over radical n. Right. X bar, 2.6 minus mu 2.68 over 0.32 sigma over radical 30. Okay, so 2.6 minus 2.68, okay, that's negative 0.08, divided by 0.32 divided by the square root of 30. 30, right? Yeah. Negative 1.37. Okay, now, is this a true statement? Is negative 1, come on now, people. Come on now, people. Is negative 1.37 less than negative 1.645? No. We fail to reject. Okay. So again, you write the statement out, and again, I think we got a little lazy, like on the last test or so. Make sure you write that statement. Not enough information to reject the claim. That's an O. To reject the claim that mu is greater than or equal to 2.68 at alpha 0.05. Sorry for the poor.
It looks so good.
That's a greater than or equal to symbol.
Oh.
That's a 5.
I thought it was a funny equal sign.
It is. It's a greater than or equal to.